Okay, it's just basically glorified office hours. So you're here, I'm here. There's no reason to wait. If you have questions, I'll just answer. Okay. Or if you have any specific topic you want me to go over.
What's the first topic saying?
Hashing and applications.
And does that include streaming stuff?
That's very baby stuff, right? You know, I mean, focus more on understanding randomization than the specific concrete details of some things, right? You need to know fingerprinting a little bit. You need to know the very basics of streaming, right? But you need to know what expectation is, what variance is, how to calculate those things, probabilities, right? More at that level, right? And then the basics of hashing, right? What is hashing? How do you do hashing? Okay. Any concrete questions from the sample exams or homeworks or like?
Are the example exams posted on the Piazza?
Sorry?
Are there the example exams that they're posted on the Piazza? Is that where we can find them?
Yeah, we posted some, right? I mean, I posted an old one from when I taught 573, let's see, yeah. So this is one, and so Patrick posted links to spring 2006 and spring 2005, and I think Jeff taught 473. So if you want to look at some problems. So let me, okay.
Can we talk about number 6, the assignment problem?
Which one? In this one?
Yeah.
Okay. Let's see. Okay. Okay.
It's kind of similar to one of the homework problems that
Yeah, okay. There are m tasks, T1, T2, Tm, that need to be assigned to n workers, right? P1, P2, Pn. And for each task, basically, and worker, there is an integer weight. This denotes the weight of assigning task I to worker j. For each worker, basically, there is an integer valued lower bound and integer valued upper bound on the number of tasks that we assign to Pj. Moreover, for the sake of redundancy, each task to be assigned to at least 2 distinct workers. Okay, and a feasible assignment is one that assigns all tasks respecting the above mentioned constraints. Okay. Okay, so first, let's see. Okay. And then given numbers W1, W2, describe an efficient algorithm that checks whether there's a feasible assignment in which a task Ti is assigned to worker Pj only if W1 is less than equal to Wij is less than equal to W2. Okay, so I mean, what is the basic setup, right? So you first have to understand, it's a basic setup is, okay, whenever you have an assignment problem, you say, okay, there is think of a bipartite graph, right? So we are trying to assign tasks to workers, right? So, I mean, you think of tasks and workers, right? All right? Agreed? So, okay, you create one node. You start with some basic setup. Okay, so let's say there are m nodes here and one per each task. Okay, and n workers, and so this is task I, and say this is worker J, right? All right. In the basic setup, anybody can be assigned to anybody, right? There wasn't any constraint which told you that task I cannot be assigned to worker J, right? So in some sense, in that setting, the graph is complete graph. That is, anybody can be assigned to anybody, right? Okay. So so we can create a complete graph, right, in the beginning. Okay. And with what are some constraints we wanted? We wanted to make sure that each worker had at least some number of tasks assigned, and at no more than some other number of tasks assigned, right? So what we wanted to make sure was there is an interval Lj, Uj for each worker which says, I have to assign so many tasks, right? Okay, and on the left hand side, what did we say? That every job or task has to be assigned to at least 2, right? So okay, that means that this interval is to infinity, right? That is, at least there is a lower bound of how many times a task has to be assigned, and an upper bound you can assign as many times as you want if you want to satisfy the constraint. So the upper bound is infinity. Okay. Okay. So that's the basic setup. So but then we have basically, you should think, I have lower bounds, upper bounds. So I should think of modeling it as some kind of a lower bounded flow or circulation, right? So how would you do it? What would you add to make sure that, what problem would you, you have to solve it using eventually some kind of a flow problem, right? So what else do you need to add to, suppose I just say, is there a feasible assignment? Okay. If you have no other constraints, right, this is an easy problem, right? Why? Because it's a complete graph, right? It's not very difficult to find a feasible assignment. Why?
Because you can like treat any edge. You can say any edge is.
So my constraints are every task has to be assigned at least 2 times, right? And every worker has to have some number of lower and upper bounds. It's not quite obvious actually. Even with the upper bound constraint, it's not obvious that you can do it so easily. If I didn't have upper bounds on the workers, then it is easy, right? You make sure you load everybody enough, right? But if you have upper bounds, it may be a little tricky, right? Okay, so how would you solve this? If I just say, is there a feasible assignment? Via flow, how would you solve it? So you add a source and sink, right? Source and sink, and you connect the source to this, right? And sink to this. And what about which way do you orient the edges? Right, you go this way, and all of them go this way, all of them go this way. Okay, now what are we trying to satisfy, right? What should we put on the arcs? What capacities do you want to put? Lower bounds, upper bounds? Yeah, what will you put on S to task I? What should we put? Lower bound, upper bounds, what should you put? How much should you put and what should you put? Yeah, you put 2 infinity, right? That corresponds to, right? What about on the other side? You put Lj, Uj for each, right? Okay. Now what about in the middle? Sorry? Do you want to put 1? Yeah, it depends on your think, right? Do I want to put 1 or I don't want to put anything, right? Okay, what does putting 1 mean? It means that I'm allowed to assign a task to a person only once, right? That is, remember I'm requiring each task to be assigned twice, right? So now you have it's a small modeling question. Do I want to assign 2 copies of the same task to the same person? But then you have to look at the problem and say, what did the problem actually say? It says, moreover, for the sake of redundancy, each task has to be assigned to at least 2 distinct workers. Okay? So if I don't put 1 on the arcs in the middle, then I may assign 2 copies of the task to the same person, right? So I should put 1 on the middle, right? Okay? It depends on the question, that is how you want to model, right? Okay, so you say, okay, and I put 1 on all these things, and then I just put, now when I have lower bounds, it's most natural to think of circulations, not flow. Okay, so you say, okay, you put an arc here, and what do you want to put on this, right? What are the lower and upper bounds you want to put on this? You can actually, in fact, I say, you just put 0 infinity. You don't care about this arc because you already put lower bounds on the other arcs. They will ensure that 2 copies are assigned, right? This is just to make it a circulation. Okay? So I don't really need, I don't need to know how many I need to assign because it depends on these constraints and these constraints, right? I don't quite know how many have to be assigned in this problem, right? So I don't really care. So this ensures that, a circulation in this ensures that at least 2 units of flow will go through this, right? Okay? That's what the lower bound. Suppose I find a feasible circulation. Then 2 units will go and, maybe more than 2 will have to go. Okay, I don't know, right? At least 2 will go, right? And then, that flow has to go this way. So, there is only one per edge here. So each task will be assigned to at least 2 workers, right? Whatever flow comes in has to go out, and it's all integer flow because the capacities are all integer, right? So it will be assigned at least twice, okay? And then, this constraint ensures that we get at least from each j to t, it ensures that at least Lj tasks are assigned and no more than Uj tasks are assigned because we have a lower and upper bounds, okay? And, depending on what other constraints are, that determines what happens here, okay? So if there is a feasible solution to the circulation problem, you get a feasible assignment to what you wanted, right? Okay, but if there isn't, the conversely, if there is a actual assignment, you can convert as a feasible circulation also, right? You look at the assignment, assign them, put 1, 1, 1, 1 on that, and then you can easily see that if there is an assignment, then there is a feasible circulation in this problem, right? In this flow network we created. So it's if and only if, right? It's intuitive, but if you want to go with more formal, then you have to prove it formally, but you can see, right? I can convince you, right? So this is what you do, right? But that's the basic setup. And then the first problem is saying, this is adding one more twist, right? Just to, what is it saying? It's saying, in fact, it's simply saying, when, it is adding some restrictions, saying, when can I assign a task I to a worker j? It says there are 2 numbers w1, w2, if and only if wij, I give you the information up front, wij is the cost of assigning I to j, right? It says, you can only assign I to j if wij is between w1 and w2, right? So what do? You just change this graph. You are allowed to assign this only if wij is in between those 2 things, right? So you remove some edges from here, or you only allow edges between I and j if that condition is satisfied. So what this means is that I'm going to kill some edges here, right? Okay, so your assignment has to respect that additional constraint, right? So you start with this graph and say, oh, if the edge, if wij is not in the range w1, w2, I remove that edge. That means I'm preventing you from assigning I to j in that case. That's what you do, right? So you're getting a subset of these edges now. So which is still fine. The problem is still, nothing changes, right? You're just removing some assignments cannot be done, so you remove it. Okay? It's more or less simply saying another way of saying, I'll tell you whether you can assign I to j or not, right? Okay. So that's it. There's nothing complicated in that. Okay, now it is a little bit different. So, okay, use the above algorithm to solve the balanced assignment problem in which the goal is to find a feasible assignment with the minimum balance. Okay, so what will you do? W2 minus W1 is the range, right? The balance in which you can assign, right? Okay, so what did you solve in this part? In this part, if I give you a B, okay, if I give you W2 and W1, you can check whether there is an assignment satisfying that constraint, right? Okay, now I'm trying to squeeze those W2 and W1 as small as possible, right? Okay, you can think of this as an optimization problem where you already solved the decision problem, right? Okay, so you want to find W2 and W1 with a minimum W2 minus W1 such that there is a feasible assignment, right? Okay. So let's do something very dumb, right? I mean, think of this as, reducing optimization to decision. So you want to find the W2 and W1 such that, how can you do binary search? Suppose you want to do binary search. Okay, do you want to see an example of a problem instance or, okay. Not. Is the problem, did you understand the problem? That's the first question. If you don't understand the problem, trying to solve it is hard.
I don't really know I still don't really understand what it means by balance.
Yeah, so see the math, right? The math is like, what the math is saying is, so look at this problem. What do you understand from this? What is the input to this part A? The input to the part A is the following, right? The input to part A is, I give you this thing, right? The number of tasks, number of workers, and we already have this upper bounds and lower bounds, but for every I and j, I'll also give you a number, wij, right? And then W1 is a big number, W2 is a big number, W2 is another number which is bigger than W1, and I'm only allowing you to assign I to j if wij falls in the range W1, W2, okay? And I want to, if you take W2 to be the maximum of all the wij and W1 to be the minimum of all wij, then what does it mean? Then am I constraining you at all? Suppose I tell you W2 is the maximum of all the numbers and W1 is the minimum of all the numbers. What does that mean? It means I'm allowing you to assign anybody to anybody, no? Okay? So so it's a complete graph. Nobody is restricted, so it's, right? But if I keep reducing W2 or increasing W1 from those extremes, what happens? I'm preventing you from assigning certain people to certain things, right? Yeah? And as I do that, maybe I won't be able to assign anybody, right? Okay? Okay, so let me ask a simpler question first, okay? When you have a little bit of difficulty with two parameters, let's do it one parameter. Suppose we fix W1 to be always 0 for simplicity, okay? Then I'm asking what is the smallest W2 such that I can actually find a feasible assignment. Does it make sense? Right? Okay, how will you do that? Okay, let's solve the restricted problem, right? The restricted problem is take W1 to be 0, right? I'm saying what is the smallest W2, right? That's what I was asking, right? What is the smallest W2 such that I get a feasible assignment? Right?
The largest value weight for any of the tests.
No, I don't know because it depends on, so here is what, I mean, if for a given W2 you can check whether there is a feasible assignment using the previous algorithm, right? By solving the circulation. But now you want to find the smallest W2, right? So what you can do is, you can do binary search, right? Okay. You start with the W2 which is maximum of all of the Wij is not preventing you from assigning anybody to assign anybody else, right? So you can say, aha, okay, I can start with the maximum number Wij for W2 and then do binary search, right? Does that make sense? 0 to W2, right? You do binary search. And at the smallest value of W2, when my feasibility says yes, that's the minimum value of W2. Yeah? Does that make sense? Yes or no? Yeah? Okay. What is another way of doing it is less interesting than binary search, but still is pretty okay, polynomial time. Because I can try all possible values of Wij, right? Yeah? Because what will that number be? That number is going to, when is it not going to be feasible, right? Think of when it is not going to be feasible. Why is it not feasible? It is feasible at some point. When I moved it a little bit below, it is not going to be feasible. When I moved it a little bit less, it is not feasible, right? So that number when it stops must be one of the Wij, right? At some point I prevented somebody from being assigned. So I can try all possible Wij as a candidate for W2. And whatever is and that's so that only n square or nm distinct, the number of inputs Wij is only n times m, right? Because for every I and j I give you a number, right? So you try all of them and find the minimum value of W2 for which that is feasible. Yeah? Agreed? So that's it, right? You first check the feasibility problem and then you try the values of W2 at which this works. Okay, now he has a little bit of a different problem. I have W1 also and I'm trying to minimize W2 minus W1. From the previous idea, can you figure out how to do that? This more general problem?
It's like a golden section search type thing where
you can do that, or from this simple idea, you check all Wij pairs. I mean, if you just want brute force, check the one value of Wij, another value of Wij, right? And check within this interval whether it is feasible. Okay, and among all such pairs, feasible pairs, pick the one with the smallest difference. You're trying all possibilities, right? Of course, it's inefficient. It is, nm times nm, right? There are so many values of Wij, but still it's polynomial time, right? It's a dumb algorithm, but if you want to do more clever, you can do binary search again, right? You can do this. You can search on the difference of the value. You can do something clever, but you don't have to do anything clever here. You try all possible values of Wij pairs, and among them choose the one with the smallest range, right? And each time you invoke the decision algorithm. Is it feasible or not feasible? Okay? Yeah? The second part is a bit trickier, right? It's not so obvious what to do, right? Right? But the first part is the thing, I mean, it's a 573, it is a grad level course, so the second part is a bit harder. But the first part is basically, I have an assignment problem, I have lower bounds, upper bounds, okay, what are the constraints? You just have to understand how to model the constraints using a basic simple assignment thing, right? It's mostly about understanding the constraints and modeling it rather than worrying about what algorithm you're going to use, because the algorithm is there, flow, lower bound, circulations, right? So that's the thing is to understand what am I assigning to what? What constraints are there on my assignment, right? So main thing is, should I create copies? What capacity should I put in the middle? Should I put 1? Should I put 2? Infinity? Should I create a copy like in the homework thing, right? Right, So that is, you're really thinking about modeling using assignment and flow rather than figuring out a specific algorithm to solve it. You will eventually use the standard algorithm, right? So it's a reduction, right? It's a reduction. Yeah. Yes, any other questions?
Can we try Spring 2016 problem 2?
Yeah.
Spring 2016. Problem 2.
Problem 3?
2.
2. Okay. Okay. I haven't looked at it before, so I have to figure out. Quentin, Alice, another. Can you see this? Read it? Or do you need to zoom it? Or do I need to let one more? Okay. Okay, so what does it feel like?
It's an undirected graph.
No, it doesn't say it's undirected, right? Where does it say it's undirected? So, okay, what is the second, I mean, what does the second part of the problem kind of tell you, right? Jeff likes to give this, Sariel also, this crazy looking problems where, my style is not, I'll ask you directly, here is a graph, here is this, here is that, right, but this year like, okay, you have to figure out what is being asked, right? Right? So what does it feel like to you though? Say, what is the second paragraph? Some flow problem, right? Jeff gives a hint eventually, right? That there is. Okay, so but you have to then go back and say, okay, there's a graph, okay, vertex and a fountain and an edge for each gate. But what is the gate saying, right? During those 5 minutes, okay, anyone passing more than one gate in the same 5-minute period will turn into a, okay. Okay, so let's create a graph, okay, and, okay, okay, so basically it's saying, okay, let's see, is there any more to the problem? Okay. Anyone attempting to pass through more than one gate in the same 5-minute period will turn into a niffin. Okay. Okay, so we create a graph G, and what is Earth fountain will be the S, right? Yeah, and Fillory fountain would be the sink, right? Okay. Okay. So what is okay? During those, if more than, okay, so 8 showers, right? You're also given a positive integer in 8 showers. The maximum number of people that can walk from in 8 showers. Okay. Okay. So a gate is an edge, right? So you don't want more than one person to use an edge, right? Okay, so so people can pass through different gates at the same time. So if they, what is it suggesting to you?
The edge capacity is 1.
Edge capacity is 1, right? So if two people, okay, so okay, okay, so how will a person go from S to T? So they have to go through some edges, right? Okay, so edges correspond to gates, right? So okay, so let's look at the person, one person going from in that 5-minute window. There is no time, so you can so it opens for 5 minutes or like, right? If how many people can go simultaneously? No, I mean, but says one person can go in one path, right? Right? Okay, but another person can go on a different path, no? So what is it being? How can two people go simultaneously? Only if their paths are edge disjoint, right? Right? Agreed. So if you want to send a lot of people in, how will you do it? Right? What it's saying is that you want to send maximum number of edge disjoint paths, right? Okay. So basically, if you have this graph S and T, then the maximum number of edge disjoint paths between S and T is the number of people you can send in that 5 minutes, right? I mean that's 5, right? Okay.
It doesn't have to be edge disjoint, right?
Why?
It only says they can't pass through the same gate at the same time, but maybe someone takes this edge and then an hour later someone else takes that edge.
Yeah. No. So think of in the 1 5-minute interval.
Oh,
Okay. Yeah. So next, that's whoops. Sorry.
It's kind of misleading. Does it just mean that like your end result is the min cut max flow algorithm?
Yeah.
5 times age?
Yeah, exactly, right? So it is 5, no, not 5 times h, I guess. Oh, once an hour, okay, it opens, right? Yeah, exactly, right? So basically, h times the max flow, right? In per 1 hour, how many can you send, right?
But each person can only go through one gate in an hour.
No, but it is open only once an hour, right? No, isn't that clear?
Anyone attempt to pass through more than one gate in the same 5 minutes. So each person goes through one edge.
Only go one edge.
Well, it doesn't say that anywhere.
Oh, wait. Moreover, anyone attempting to pass through more than one gate in the same 5-minute period will turn into a niffin. Aha, I see. Wait, now this is
If the shortest path has length greater than 12, I can't even, greater than h, I can't even send one person.
sorry?
If the shortest path, SD path is greater than, has length greater than h, then I can't even send one person. Because each time each person is moving by one edge.
Or anyone attempting to pass through more than one gate in the same 5-minute period will turn into a niffin. Okay. Okay, so let's see. Okay, so let's see what one person can do. Okay, so how will okay, during the gates are open only for 5 minutes every hour, all at the same time. Okay, during those 5 minutes, if more than one person passes through any single gate, The piece to I see. Okay, I see. In H hours, okay. In the same 5-minute, okay. Okay, so let's look at how a person will go from S to T. What should they do? They should start at S, then do what? They can go from S to, let's look at H hours, right? Okay. Basically, how does their traversal from S to T look like? In the first hour, it is open for 5 minutes, right? Some window. So they can cross one edge, basically. And then what will they have to wait, right? For the second hour, right? Okay? And then they can go, right? In the second hour, they could go to another, one more gate, right? In the third hour, they could go one more gate, right? Right? Okay? So, they can only go H gates basically, right? Yeah? Okay. So, what we could, if you look at, this is what I'm guessing, that's why I'm not a big fan of very complicated constraints, which is hard to interpret sometimes, especially in an exam, right? Okay, so here is one. So let's create H layers, right? Okay. So if you look at S, a path from S to T in this H-layered graph, right, would correspond to going from S to T, right, only one gate per hour, right? So that's my understanding, right? I admit that I am having a tough time understanding what exactly is being asked here. Because it's not very formal. Different gates at the same time. Okay. So at the same time, Okay. So basically, this is what it is. It appears to be, right? You create, hours are, so basically think of instead of 5 minutes an hour, think of like, I have H time steps, right? Because it's open, the gates are open only once per hour, okay, and it's open for 5 minutes, but you can only go on one edge anyway in that time period, right? So what you're saying is that, what will each person do? In the first hour, what will they do, right? They can cross one edge, right? And the constraint says that you can't cross two edges in that 5 minutes because then you will turn into a niffin, right? So you cross one edge in 1 minute, okay, in that first hour, and then you have to wait till the gates open again, right? So you cross another edge in the second hour, right? So second time unit, and another edge in the third time unit, till you reach the sink, right? Okay, at some point you will reach the sink and you go away, right? Okay. Moreover, if I want to use this edge in that time unit, you can't use that edge. Okay, right? If two people come are at the same vertex, say at the same S, both people can't use the same edge at the same time, right? So it is enforcing disjointness, right? Edge disjoint paths. We want the maximum number of edge disjoint paths, right? In some graph. Now the question is, what graph is that? Okay? Okay, so let's model time H hours as H copies of the graph. Okay? Okay, so I'm saying, this is V1, it's the same copy, right? V2, V3, VH. Okay. What does it mean that, I started S, right? And I create, in this initial copy, let's say V0, okay, only S has edges. And from here to here, if this is a copy of U1 and this is a copy of V2, I put an edge if there is an edge between U and V in the original graph. Okay? Right? Now, I want to claim that I find them, okay, now we have to be a little bit careful, right? What should I connect to the sink? Okay? Right? So you have to be a little bit careful because there is a copy of the sink in every copy, right? So I'll connect all copies of T in everything to one super sink T star. Okay? Okay? And then I claim I find the maximum number of edge disjoint paths from S to T star in this graph. Okay? So what does it mean, right? What does a path here mean? A path here means that I start at S, go somewhere, come and go there, right? Edge disjointness guarantees that, what am I doing? So if you look at any particular time, right, two people are not using the same edge, right? Because the paths are edge disjoint. Okay? So, but I may be able to reach T in 2 steps, in which case I don't care, I'll disappear, right? I'll leave the thing. So this is the thing, you're modeling time using copies of the graph, and you're using the fact that, you can't use the same edge by 2 people using edge disjointness. So the maximum number of edge disjoint paths in this graph would correspond to the number of people who can go from S to T in H hours. Yeah? Does that make sense or no? Yeah? Yeah.
Do we need to add an edge between each 2 layers between the same node to model someone staying in that node?
Yeah, you need to add, sorry, that's a good point. Yes, you need to add that. Yeah. You need to add that if somebody can stay at the same place, right? Yeah, they have. Yeah, that is important. Yes. Okay, if you forget it, -1, not a big deal, right? Okay. The more important thing is okay. All right. Yeah, I think that's what I understand from the problem, right? Yeah, this is a little bit tricky problem actually. Yeah. Okay. See, the power of graphs is really in the modeling. Okay, you can do many funky things with graphs, right? And that's part of the. Okay, what else? Any other questions? Yeah, is the number 4 okay? Did you do 4? It's more easily modeled as a standard. No? Anyone?
I think we just break each node into 2 and
Yeah, so
I mean, first it's the undirected graph. We need to
yeah.
add two edges to change it to directed graph, and then just find the node disjoint path by breaking each node into two.
Yeah, so I mean, you know, so I mean, it's somewhat conceptually easy to not necessarily go through the reduction first, but to think just in undirected graphs. Okay. So basically, what you do is, you know, you say, okay, connect a super source to all the terminals, and then a super sink. I mean, you assume without loss of generality that none of the terminals is on the boundary for simplicity. Okay. I think he didn't specify that, but just simply assume that no terminal is on the boundary, right? And then you just want to know, and you connect a super sink with edges to all the boundary vertices, okay? And then say, you know, so basically S connects to all the terminals, all the boundary vertices connect to T, okay? And then you simply ask, you know, what is the maximum number of node disjoint paths from S to T in this undirected graph? Okay, you know how to solve that, okay, by reduction, right? You don't have to specify that, okay? You can solve the maximum number of node disjoint paths between S and T in an undirected graph, okay? That's a black box because we already saw how to solve it using flow, okay? Okay, that will solve this problem because, you know, and then you say, you know, is that equal to the number of terminals? If that is equal to the number of terminals, then what did we find? We found paths. We start at S, go to a terminal, right? You know, because every terminal now is connected to a boundary, and they all have to be disjoint, node disjoint, right? Okay. So it's not enough to solve the maximum node disjoint path problem. You have to say, you know, if it is equal to the number of terminals, then we know we can do it. Otherwise, no, right? Okay. So it's just a reduction to maximum number of node disjoint paths in an undirected graph. There is no, you don't have to go through the directed graph reduction unless somehow there is some, right? Oh, so do you remember, I mean, this is just, how do you prove that every regular bipartite graph has a perfect matching? Just as a way to remind you about matchings, okay? So remember, I briefly sketched. So here is suppose I ask you to prove this. Prove that every regular, what is a regular? What do you mean by regular? Regular, that means they have the same degree. All have degree, same degree, right? D, some D, okay? Has a perfect matching. Okay, Hall's theorem. What does Hall's theorem say? You remember that? Okay, you don't even have to use Hall's theorem. You can use a simple flow. There's a cute proof using simple flow. What do you, okay, so let's think algorithmically. What do you need to prove? You need to prove that you know when there is a perfect matching, right? Or you know how to compute a maximum matching, right? Okay, how do you compute a maximum matching? You say, aha, okay, I have left, I have right. I create this, I rate, and I this, S and T and okay. The problem here is you don't know what the graph is, right? You know how to compute it algorithmically, but you're trying to prove that every regular graph has a perfect matching. So if it has a perfect matching in this reduction, how much flow should there be? Sorry? Yeah, that's true. But if you want to prove that a graph has a perfect matching, then if the number of, first you have to verify that the number of sides on the left and right are the same. That's easy to see, right? Because the degrees are the same. So okay, you know that there is n and there is n here. Okay, you want to prove that there is a matching of size n in this graph, which means that you want to prove that there is a flow of n in this graph. How can there be a flow of n in this graph? Well, if and only if there is 1 unit on all of this, right? Okay, and 1 unit here. Okay, so you want to know, is there a flow of 1 unit on all of those things? But you don't know the graph, right? How will you convince me that there is a flow of 1 unit? Okay, in this graph, but what do you know? They are all, every vertex has d, it's d regular for some d. Okay. But you have to send 1 unit of flow here, and you have to send it out, right? 1 unit, right? How can you send 1 unit? It's like, I don't know. What will you do? I don't know where the edges are going. But what do I know? I only know that there are d. Everybody has exactly d edges. How much should I send on each edge? Sorry? Yeah, send fractionally, don't send integrally, right? You don't know because perfect matchings are, okay, you say 1 over d I'll send on each of those edges. Okay, but now you say, wait a second, I'm sending 1 over d on each of those edges, but what happens to the other guy on the right hand side? Is he okay? He's okay because he has exactly d edges coming and, okay, and he can send it out, okay. Right? So you can say, okay, I can send 1 over d on every edge and it's a feasible flow, right? I don't even know what the graph is, right? But whatever the graph is, I know it is going to be feasible, right? So I showed you, what did I show you? That there is a flow of value n between s and t in this graph. Then you know it must have a perfect matching, right? Because I can convert that, this fractional flow, right? It's not integral flow. But I know if there's a fractional flow, I can convert it into integral flow because it's integer capacities. So I'm proving to you there is a flow of value n in this graph, right? Which means I must have a perfect matching, right? Okay, you can also use Hall's theorem, right, to prove this. But if you see, that's a nice thing about fractional implies integer, right? So I didn't give you an integer flow because I don't know the graph, so I can't give you a matching because how can I give you a matching, right? Because I don't know the graph. I only am able to prove that there exists a matching, right? So that's a bit strange statement, right? Because without knowing the graph, how can you? Well, you have to use the conditions on the graph, right? That it is deregular. So I'm just using the bare minimum that everybody has the same degree by sending a flow like that, right? Whatever those edges are, okay? You can also use Hall's theorem to prove that. Same thing, right? In Hall's theorem too, we didn't know the graph, but we were still able to prove that as long as for every subset on the left-hand side, the number of neighbors is at least the size of that subset, there is a perfect matching. There too, we use this kind of proof, right? We use a min-cut argument, but we didn't use flow, but we just use min-cut argument. Here, we're explicitly using flow, right? Right? So that's a nice thing about this algorithmic constructions and maximum. Okay. Yeah. So let me ask you one more question just to get you thinking a little bit. Okay, let's see. Maybe to make you think a little bit about randomness. Why don't you try one part A? Let's see if you can do that. So when you think of an ideal random hash function, it just means it's like think of it as throwing balls into bins, right? Right? If you pick a hash function come from a set of all hash functions, what does it mean, right? If you look at all hash functions, the ideal random function, that's inefficient. We don't do it because we can't compactly represent hash functions of all hash functions. Okay? Computationally, but it is just for analysis sake. Whenever you think of ideal random hash function, you mean that you're throwing items randomly into bins, right? That's what it means to be an ideal hash function. It's not practical, but it's just to help us think, right, a little bit. So it's basically asking the following, right? You know, you have a hash table of size m, and you have n items you're hashing. That means that you're throwing n balls into m bins, right? And then he's asking, you know, how many collisions will there be? Expected number of collisions. Okay. So that means sorry?
If we have three things of the same hash value, that will give me three pairs of collisions.
3 pairs of collisions. Sorry? N over m. Okay, how? No,
Well, it's like what she said. Like if you have one spot and you have three things, then I mean that's not a proof. That's just an example. That's how I
okay. So, but think of it like this, right? You know, instead of thinking about, so look at a particular x. Okay. You look at all. What is the probability that another item will collide with it? So took x has to go somewhere, right? Okay, now fix x, you know, it's somewhere, it doesn't matter where it is, right? It falls into one bin, right? Now how many other items will fall into that bin? I mean, each of them will give it one collision, right? Okay, let's count for every item how many things it collides with, right? So if I look at one item, you know, and say, what is the probability that, so I am sitting in bin 1, say, without loss of generality, right? Everybody else is being thrown into bins at random, right? So what is the probability that, you know, say a fixed guy will, say, hit me? I mean, it will fall in the same bin, right? It is a probability falling in the same, say it's bin 1, right? Because I am sitting in bin 1 without loss of generality, then that guy will hit me, will fall in my own bin with probability 1 over m, right? Right? So the expected number of items that will collide with me is what? N over m, right? I mean n minus 1 over m basically, right? Because n minus 1 m, alright. Okay, so now you have to sum this up over what? For every item, you know, if you sum this over every item, what do you get? I mean, you're counting, I mean, these are only the collisions for this guy, right? Okay, now for by symmetry, everybody will have the, I mean, it's the same argument for everybody, right? So, if you sum it up over all the things, you know, what will you get? N times n over m, n minus 1 over m, right? But we are double counting, no? Yeah? Because if x is collided with y, we will also collide y with x. So it is n choose 2 divided by m. That is a different way of counting it, right? Okay, look at any pair. What is the probability that they will both land in the same bin? 1 over m basically. So that's another, right? So when you are not sure, you have to go very slowly and say, you know, I will do it step by step rather than make a guess. Right, you know, because it depends on what is being asked, right? Okay, the average number of balls in a bin is n over m, right? But that's not the number of collisions, right? If you ask how many balls are there in bin 1, and what is the expected number of balls in a specific bin, it is n over m. Okay, but that's not the number of collisions, right? So it depends on what is being asked, right? So you have to slow down and say, okay, can I count it this way or can I count it that way? How do I count it, right? Or you can say, look, let me look at a single pair. What is the probability that that pair will form a collision, right? Right, and there are n choose 2 things, right? Yeah. So yeah, if you give me x and y, that's another way of doing it. If you have a pair x, y, what is the probability they will form a collision? Well, x goes, say, first without laws of generality. Then what is the probability y will fall in the same bin as x? It's exactly 1 over m, right? Okay, there are n choose 2 pairs. So the expected number is n choose 2 times 1 over m, right? That's another way of doing it, but I did it a different way, right? But both are okay, right? Right? It depends on how you count. Okay. Okay, how do you estimate the probability that there are no collisions if you use Markov's inequality? So here m is much bigger than n, right? Otherwise you will have a lot of collisions, right? So what is the expected number of collisions? We just counted it, right? N choose 2 over m, right? Okay, n choose 2 over m, it makes sense to not have collisions only if n choose 2 over m is less than 1, right? That means that there is some probability of no collisions, right? So he's just using simple Markov inequality. Suppose m is very big, m is n cube or something like that, right? Then what is the expected number of collisions? N choose 2 over m. So it is n square, roughly n square over m, right? If m is very big, then that is very small, right? If you have m is very big compared to n cube, n to the 4, right? Then you would expect very few collisions, right? But by Markov inequality, what can you prove, right? What does collision mean, right? Collision means at least 1, right? Okay, the expected number is n choose 2 divided by m. What is the probability that the expectation, you will exceed the expectation by, so you want to calculate the following, right? So let x be number of collisions. This is number of collisions. It's a random variable, right? Yeah. So we just calculated that expectation of x is what? N choose 2 over m, right? Which is n times n minus 1 by 2m, right? Okay. This is the expected number of collisions. So we are asking what is the probability that x is equal to 0, right? Okay, but this is the same as probability that x is less than 1, right? X, because it's an integer value, right? So what is this by Markov's inequality? If you just want to use Markov's inequality. Sorry?
1 minus probability.
Yeah, but how will you apply Markov's inequality? Okay, yeah, you have to apply it, you have to say 1 minus probability x is greater than or equal to 1, right? Okay, what is probability x greater than or equal to 1? Probability x greater than or equal to 1 by Markov's inequality is less than expectation of x divided by 1, right? Okay, expectation of x is what? Right? So, if you use Markov's inequality, you will get something interesting only if m is very big. Otherwise, you will not get any interesting thing, right? Okay. So, if probability, if x is say m is n cube, then this is what? For simplicity, so this is 2m. 2n cube is less than 1 over 2n or something like that, right? I mean, so then you'll say, the probability x is 0 is at least 1 minus 1 over 2n. Okay, you'll get interesting result in using Markov's inequality only if m is very large, right? You're not able to calculate the exact probability. It's very hard to do that, right? Okay, so that's how you do it, right? Okay. Yeah, so this is the same thing, right? C is asking what is the estimate the largest value of n such that the probability of having no collision is at least 1 minus 1 over n. Okay, now we calculate that, basically we calculate that we choose m to be n cube, you'll get that, right? Or right? If m is n cube, you'll get the probability is no collisions is at least 1 minus 1 over n. So that means basically m should be at least n to the n cube, yeah. So m should be at least n cube, or if you want to the other way around, n should be 1/3 m basically, m to the 1/3, not okay, yeah. All right. Any other questions? Any problems or any conceptual things? Okay, let's see if any other. I mean, let's see if there are any other interesting questions in spring 2005. Anything else, or should we call it a day? Yeah, question? No. Yeah. This question is not relevant because we didn't do trips and stuff. I don't remember what this question is. Yeah, if you want a couple of hashing questions, you can look at this. Just right.
For number one, it's the easiest way to calculate the max flow and min cut. Just to, I mean, it's you kind of do you just take the residual, or is there another way of doing it manually?
Sorry, yeah, I mean, in fact, the easiest way to compute the min cut is to compute a max flow. Not easiest, I mean, that's the only way we know. I mean, that's not true, but I mean, we have other ways of computing min cuts using a different structural characterization. But min cut is hard in general, right? I mean, if you try to find a min cut, you'll try enumeration basically, right? And you can always go wrong with it unless you systematically enumerate. While with a max flow algorithm, it's easy to check if you have a flow, you can do augmentation, right? It's easy to draw the residual graph. It is a very systematic algorithm, simple algorithm, and you're just checking paths. So in this graph, what I would do first is, okay, how I try to find a max flow, right? What algorithm will you use to find the max flow if you have a heuristically on this algorithm? What will you do? Right, but how? You have a choice of which path to pick, right? What would you do? We discussed an algorithm which we know is polynomial time because it does something nice. So in the first iteration, what path will you find? The minimum, maximum bottleneck capacity path, right? So what is the maximum bottleneck capacity path in this graph? What will the top one be? 453? Yeah? Okay, but that will means you can send 3 units of flow on that. There's a path which you can send more than that.
The 6446?
Yeah, 6446, right? You know, this one. Right? You can send 4 units on that path, right? And then then you compute the residual graph of that. Okay? But you can also send 453, right, in that because they're disjoint paths. So in one shot you can send 6, 4, this would give you 4 units and that would give you 3 units. Okay, and then you can do that right away and then you kind of find the residual graph. Well, okay, now then you can easily see that I can send 2, in fact I can send 2 also, right? So you can get a flow of 3 plus 2 plus 4 already. And then, you know, you have to do residual graph. I don't know. I have to do the residual graph and then you will be able to quickly find a max flow. Right? And then you can, and then in the residual graph, how do you know it's a max flow? Yeah, in what, right? In the residual graph. That's why he's asking, you know, in the residual graph, if you still have a path, it means you have not reached a max flow. Okay? But, okay, then how do you find the min cut? Yeah. In what graph? In the residual graph, right? You find all the, not in this graph, but in the residual graph of a maximum flow, you find all the vertices reachable from S. That will form a min cut in the original graph, right? So that's how you find this, right? So it's really saying, you know, can you run the augmenting path algorithm on a small example, right? And remember the facts about max flow and min cut and stuff, okay? Yeah. Okay, I think we are getting close. You know, unless there are more questions, you can also ask in office hours, ask in Piazza. Okay, if you have questions about anything in these things. Yeah. Yes. All right. As I said, you know, we'll have 3 hours, but it will be only 4 problems or 4.5. A small problem. Okay. You can use it if you want, or you can go home. Right. You know, your choice. Right.